My name's Ben. I'm a software engineer at Elliptic. Just while the slides are coming up, I'll tell you a little bit about Elliptic. So Elliptic's a cryptocurrency intelligence company. So we work with banks, governments, law enforcement agencies to provide intelligence and like actionable information for them. So just to give you a bit of context, we were founded in 2013, which is quite a long time ago in cryptocurrency terms. So back then, one Bitcoin was worth $100. By the end of that year, it was worth $1,000, and we're kind of getting back to there now because I think this morning it was like 4,100. But we're not too interested in that sort of stuff. We're working on other things. So how do we provide this intelligence to our customers, and what does this look like? What sort of questions do we want to answer? So we want to talk about like, what's the source of funds for a given transaction? Where are these funds being moved to? And who controls these funds? So for example, are these funds coming from a dark market? Are they newly mined coins? Are they coming from gambling sites? Coin mixers. So depending upon your appetite for risk, you'll view each of these different types of entities different. For example, in the United States, in certain states, they're not allowed to accept money from gambling sites. So yeah. I meant to say that we have two products. We have an anti-money laundering product, which is aimed at financial institutions. So this is letting people ask, what's the source of funds for this transaction and how risky is that transaction? Should I reject this? So this allows companies to provide banking facilities to crypto users. So maybe Monzo wants to start offering accounts to businesses which are dealing with crypto. They'd need to check that the source of funds for these given crypto transactions were not illicit, or else they'd fall foul of anti-money laundering regulation in the UK. Our second product is a forensics application, which is used by law enforcement to investigate flows of funds between different entities. And I've got a little case study for you later on. And I'm beginning to regret writing my notes on sticky notes. Okay, so with this slide, I just wanted to show you that it's not just people speculating about the source, like the price of Bitcoin going up. People are actually using Bitcoin for different purposes. So on this slide, you can see exchanges, gambling sites, dark markets, crypto exchanges. In particular, you can see the flow of funds in and out of Mt. Gox there, which was hacked a long time ago now. So one specific little case study that I wanted to share with you is the WannaCry attack. I don't know if people remember this, but this was back in May 2017. It basically encrypted your files and then demanded $600 to unencrypt them. Within the application, there were 3 Bitcoin addresses hard-coded, which allows us to do the investigation. At the bottom, there's a link to a news article which said that the estimated cost to the NHS for this attack was £92 million, but when you're getting 350 million back a week from the EU, it's small change anyway, right? Okay, so this is a screenshot from our forensics app. Okay. So here we have a cluster of 3 addresses, the 3 addresses that we got from the ransomware. What you're not seeing here on the left-hand side is 300 incoming payments from people who were paying to get their files back. What you'll notice is in the next layer, there's a bunch of random clusters which they were using to obfuscate their funds, the transfer of funds. Then bizarrely, they transfer them back into one address, well, one cluster. And then they're cashing them out using these exchanges at the end, or transferring them to other currencies. the amount of currency that's been transferred here is 55 bitcoins, which at current days is 250,000 US dollars. So what would we do with this information now? We're not a law enforcement agency, so we'd hand this over to a law enforcement agency, then it becomes confidential and we have no idea what's going on. You don't know if you've had an impact, and then a few years later you read about it in the newspaper and think, oh, that's cool. So, okay, right. The challenges that we face, I'm not going to say big data, I'm going to call it lots of data, because a single machine has to be able to process the blockchain, or else you wouldn't be able to have a node running a Bitcoin daemon. The thing that makes our task difficult is we're not just summarizing the data, we're calculating risk scores, clustering addresses. We need to be able to provide answers to our customers in a reasonable amount of time, like tens of milliseconds. Just to give you an idea, like we're processing tens of thousands of risk calculations from our customers, and we're doing these about 200 a minute. But you might need to be traversing tens or maybe hundreds of hops on a very highly connected graph. Okay, so why did we choose Scala? So we started a new Scala project this year. We started a new project this year in Scala. Originally we were a Java company. So why Scala? Well, we need people who can maintain our existing code, but Java's getting more functional. It's getting a lot of features that are inspired by Scala. And with Project Lombok, I don't know if anyone's come across this, if you close your eyes a little bit, it starts to look like Scala. So if you've got to deal with Java, I can recommend Project Lombok. In addition, our ETL process is using Apache Spark. So by having our engineers also using Scala, it allows us all to work across the whole pipeline of data loading to serving HTTP requests at the other end. And it also allows us to share our knowledge with data science. So the data science team is coming up with a proof of concept. And rather than having to rewrite and productionize crappy Python code, now we just have to productionize crappy Scala code, which is a little bit better. I'm going to hand you over to Moreno now to talk a little bit more about crappy Scala code.
Thank you, Gary. Hi, everyone. Just to check how much time do we have? 10 for there? Right, great. So lots of crappy Scala code to show. All right, so I wanted to give you a quick overview of how all the good stuff Ben mentioned actually work, but especially how strong is the collaboration interaction between engineers, software engineer and data scientist. I'm a data scientist. I joined the company 2 years ago, coming with my crappy Python code, and now I write a bit of crappy Scala code. So first thing, it's true we do proof of concept, but the data science team works in a you build it, you run it mode. The output of our work goes straight into production. And if you have a small team, you have to be clever, use your resources very well, and foster collaboration with other people in the company. We engineers don't throw data at us, and we throw a machine learning model at them, and no one knows what's going on. We really work together to try to build a good product. And I'm going to start with the engineering side, so the Java side. I'm going to skip ETL, it's a bit boring. And I'll show you a tiny bit of thing we do with Scala in data science. So Ben mentioned the Java code. Our code base is basically a in-memory, high-performance, parallel graph engine. Was built in-house in the last 2-3 years. And to give you a sense of the performance requirement that we have, that we're talking about, one of the main graph computation we do is an algorithm called connected component. You may have heard of it. It's not rocket science, something very simple. We run it on the whole Bitcoin graph, which has 400 million vertices and 700 million edges. Is actually the Bitcoin address graph projection, but it doesn't matter. It runs on a machine with 30 core and 250, fits in 250 gig of RAM, one single machine, bare metal, and it runs in 8 minutes. So we are able to do all the pre-processing, at least the first phase of the pre-processing we need in just 8 minutes, which is pretty fast. And efficient graph algorithm and efficient graph traversal are really the core of what we do. And in the last years, they also been a hot topic in the market. Lots of new vendors started either to integrate in their system, or they created new products that are specifically tailored for high performance graph computation. They typically fall into big categories: single machine and distributed system. We fit in the first type together with Neo4j. We're not a software vendor, but we use that kind of technology. Neo4j released last year, 2017, a package for efficient graph algorithms that runs all in memory. Tiger Graph has been around for a while. I don't know if you heard of it. They started very recently to do a lot of marketing, and there are good benchmarks they present on their blog. And Neptune has been, AWS Neptune has been released just September this year. So I don't know if they really integrate any algorithm stuff, but surely they will soon. Right, so usually people say, you have millions of nodes and hedges, do you use GraphX? Apache Spark GraphX? No, we don't. And I recommend maybe not to do that. I mean, you don't need that. You don't necessarily need that, even if you have a big graph, because as Ben mentioned, like, a big graph is not necessarily big data. It's not necessarily a lot of data. Even huge graphs are just pair of integers, and they probably fit on your mobile phone in terms of size. And the other thing is that spreading a graph across several machines on a distributed system is just a very hard job. And it's not trivial to do it right. In preparation for this, just yesterday, very quickly, we made a comparison between our system and what you can find on the shelf, specifically Apache GraphFrame. And the algorithm we run is the one I mentioned before, connected component, applied to this public dataset from Twitter called Twitter 2010, which has 42 million vertices, which is 1/10 of what we have in Bitcoin, just in Bitcoin, and about 1 billion edges, which is twice as much we have in Bitcoin as number of edges. On the right side is some performance characteristic that we took from a presentation made at Spark Summit in 2016 by guys of Databricks, I think. They run connected component on 16 AWS nodes for a total of 250 CPU and almost 2 terabyte of RAM, which costs around like 15,000 a month or 5,000 a month if you pay 3 months up front. And we are able to run the same thing on our 32 CPU. It takes about 20 gig of RAM. For the machine of 250 gig of RAM, we actually pay $500 a month. And I can guarantee that management likes a 30x reduction of cost. 30 or 10x reduction of cost. It's quite good. And the runtime is there. It's the same order of magnitude. We run in about 14 minutes. We noticed linear scaling. We were taking sample of the dataset, so making example with a smaller amount of edges and scales linearly, very nice on a single machine. So it's 40 minutes. Databricks report 4 minutes on GraphFrame, 6 minutes on GraphX, but they have a hell lot of CPU, hell lot of RAM. you can find 20 gig on us very easily on any cloud provider. And the other important thing is that our system works for dynamic graph, so we add just a new edge, and in milliseconds we have the updated result of the algorithm. Because of immutability of the Spark system, you have to recompute everything from scratch, even if you have one single new edge, even if the change is very small. So this is issue 252 on the GitHub. It's not an issue really, it's a design aspect, but it's discussed a lot in that GitHub issue. Right, so 2 years ago, a data scientist joins, and you find the engineers, the software engineer, playing with this beast that goes so fast. And they're driving it around like a Ferrari, and they're like, my Python code is a little bit slow. Can I have a ride? Can I just go around? I promise I won't scratch it. So yeah, basically we had to decide: do we try to get data out of this amazing system we're building and maintaining, which is really the core of what we do, and make it data science friendly, make a huge CSV file or some RDD on a distributed system, an Apache graph frame, or we convert the Python guy into a Scala guy. And this is basically what happened. Scala was the perfect point of contact between the kind of analysis we wanted to do and the kind of system we had already available. So rather than joining like a big development project to create some data platform for analysis, we just built on top of what we had. It may not be the most general standard setting, but it worked very, very well for us, and is extremely effective. The setup is really easy. It's a Jupyter notebook with a Scala kernel. It's not that complicated. We wrap around the existing Java system we have, and in 2 months from inception of this new approach, we had completed analysis, and a lot of data was in the product, was served in the product to our customer. At that time was like the biggest impact we had in the data we serve. And this kind of system has been with us for years now. There are 4 main components which are there, and I'm just gonna quickly go through them. So let's jump on the Ferrari. So the first component, as I said, is Jupyter plus Scala. We take Jupyter notebook. All the data scientists know and are familiar with the Jupyter notebook. We plug a Scala kernel, and this gives us the ability to use the Java code, the Java system that is developed, maintained, and improved by the software engineers. And the other thing that we get when we have Scala is parallel collection, which are very, very nice. So we do something like, our notebook usually starts with something like, import, and then 0 until number of transactions, and now that there are 300 million, and then we just type .par. And with that CPU, everything becomes super fast and super nice. And this is a very simple, very lean, agile approach to a problem that you can do in very, very short time, really. Just Jupyter kernel, install a bunch of plugins, and you're there. It's not general, it doesn't work for every system, but it works, and it's very effective for us. And then, we have all our logic, all the data science logic, with here is just like a filter. The ... is all the magic, and I can't tell exactly what we do. I see people were taking notes of like, how not to get busted on the dark web when I buy drug. I'm sorry, I can't tell you. No one is going to look for you if you just buy drug. If you have an empire and you do like $1 million a month, then someone may be interested in you. I'm going to skip this. Right, so we got filter, maps, group by, all those nice things. They run very fast. We don't need to wait, and we don't need to worry about a cluster. We don't need to worry about talking with data engineers, bothering them. This is too slow, make it too faster. It's just working. It's very nice. But yeah, filter, group by. You can do some basic statistics. Not much. Where is that? Where is machine learning? So we discovered Smile is a machine learning library written in Scala. How many of you know Smile? No. Check it out. It's actually very nice. It's similar to scikit-learn, as the API interface is very similar, easy to use. It's quite complete. Includes classical machine learning algorithms, classification, regression, and it's pretty fast as well. It's even faster than standard Python scikit-learn. And a lot of what we do, as I said, is always start from the graph engine. So building feature and all these kind of things are done at that level. And this is just applying models. Is parallelized as well. And we're right, so we got fast graph engine, fast parallel collection, fast machine learning library. How do you visualize things? How many people know about Vegas? None. One, two, three. Where's Max? Max, I know you're there. I haven't seen your head. Because Max is actually the guy that discovered Vegas. So Vegas is a project it's created by Spotify, if I'm not wrong. And they presented a couple of years ago, I think. And there is, search for YouTube, there is a nice video that gives an introduction. And it's basically the matplotlib, the missing matplotlib for Scala. If you know if you're used to Python, you know the matplotlib, just to make nice, pretty visualization. And the nice thing is that it has a declarative language or visualization grammar. I don't know exactly how to do it. Basically, you keep the data as it is, and you say, how do you want to plot it? Which color do you want to use? Which kind of aggregation? Which kind of type of data you're using? Is it quantitative? Is nominal? Is categorical? Is time? And you can do different type of visualization without touching any data, without doing any binning, any transformation on the data. You can even do transformation within Vegas. It's pretty nice and quick and fast to do plot. Right, so that's basically our stack. It's a bit exotic somehow, but it works really well, and we like it so much that we're sticking to it, and we're not planning to move away from it very soon. Right, so take-home messages. Scala ecosystem is more mature than you would expect. Check out Vegas, check out Smile. The language allows software engineers and data scientists to speak the same language, unified ecosystem, and also help each other. It's just like your problems and your solution are just on the desk, on your left or on your right. Choose your tool wisely. In-house development is not necessarily bad. You don't need to get things out of the shelf all the time. Again, it doesn't apply to all the system, but for us it's crucial to have that graph engine. And we love parallel collection. They're so fast. And more importantly, we are hiring. So if you like the thing we discussed about, there are 4 positions open at the moment, elliptic.com/career, or come and speak to Ben, me, or Claudio that is there. All right, thank you.